So now what we want to do is we want to find the A and the B's. Like, so do you remember last semester we had the beam equations and like we had the MA, RA, C1, C2, and we found all those. Well, it's a similar story here. Now, actually last semester, remember, it was a fourth order differential equation. So you had those four constants, RA, MA, C1, C2. You needed four initial or boundary conditions. Similar story here. You need to know, well, these are second order, so you need two pieces of information. So the boundary condition would look something like this. It would look like, say, if it's maybe the value of y at 0 is, well, actually it needn't be 0, so I'm going to get rid of that. So at a starting x value is, say, y0, and the value of y at an ending point. So it's like you're interested in between x0 and x1 be y1. So that's a boundary condition. An initial condition is probably more natural. It would say that at the, and in fact I put in x's here, these should really nearly even be times. So t0 is the initial time, t1 is the final time. More natural is initial conditions, which will usually be starting at 0. And like the thing about it is, say with this one, I'll explain in a minute. So give you the derivative, which I'm going to call v0 for velocity. So with the first one, because the times are the same, you can actually do what's called a change of variables. T mapped to t minus t0. And what that'll do is that'll force these two times to be 0. So this is maybe after this. And that's just like you control the time. Like there is no time equal to 0. I mean, it's just from the start and you control the start. So that's why you can always take the times to be 0. Okay, so what these two things do is the initial or the boundary initial conditions give you equations in A and B which you can solve. So this is a similar idea to what you saw last semester, most likely with the fixed points where you got two equations in R and MA. It's most like that. Okay, so we'll do a couple of full examples here. They're long questions, they're no joke. Let's get down to it. So displacement y of t with damped harmonic oscillator with an increasing external force. So the t here, this really shouldn't be time. It's an external force that just happens. Its value in whatever units is the same as the time. So it's a bit unnatural, but there you go. The force is increasing with time. So this external force is initially, so y equal to t. It's initially 0 and it grows, it gets bigger and bigger and bigger off to infinity. So if this is a damped harmonic oscillator, eventually what's going to happen is it's going to break. But let's see what happens. So solve for displacement. So now we've got a big theory. So first you've got to do the general solution. So you forget about the initial conditions. So the initial conditions here, if we plot it on the same thing, which isn't great because they're different units, is that the initial value of the y coordinate is 1. And the initial speed, now the speed is the derivative, so it's going to start off like that. Like that. Now, because there's a spring force, it's going to go towards 0. But then the damper is going to kick in, slow it down. Then the external force is getting bigger, so it's probably going to look something like that. Maybe I'll just look ahead. Have I a picture of it? Yeah, kind of like what I said. I don't know, pretty much exactly like what I said. We'll talk about that when we get there. We're a bit away from that yet. Okay. So first of all, we have to solve the homogeneous system. So the homogeneous system is solving equal to 0. So we're looking at y double dashed of t plus 4y dashed of t plus 8y of t is equal to 0. So how you solve this first is you look at the auxiliary equation. So that's 1r squared plus 4r plus 8 equal to 0. we'll try and factorize this using the AC method. So we multiply the 1 by the 8 to get 8. Now remember, of course, you can pause me and rewind. 1 by 8, 2 by 4, 3 doesn't go, 4 I've already got. Now I can't make up 4 with this, so that means that I can't factorize. So in this case, I'm only solving it equal to 0. In the next chapter, you'd have to solve it equal to 0 and then factorize. But here, if we can't factorize it, there's no point factorizing it. Just solve it using the minus b formula. So let's see what happens. So we get r is equal to minus b, which is minus 4, plus or minus square root of b squared, that's 16, minus 4 by 1 is a, by c is 8, divided by 2. Might have a bash off the calculator there. Minus 4 plus or minus, look, it's not that bad. It's 16 minus 32, that's minus 16 over 2. And just be careful with your algebra here. Minus 4, that was nearly me talking to myself. I root 16, I suppose I'm all talking to myself in this yoke. And then root 16 is 4. So I have minus 4 plus or minus I, 4i minus 4 plus or minus I4, which is 4i, divided by 2. And so it's minus 4 over 2, which is minus 2, plus or minus I4 over 2, which is 2i. So it's minus 2 plus or minus 2i. So what we're using, therefore, is the complex root situation, which says that if you've roots p plus or minus iq, the solution is, that's homogeneous, e to the pt, in this case minus 2t, a cos q, q is the imaginary part, which is 2, plus b sine 2t. This is going to be a long question. Okay, so now that's the homogeneous solution. Now we have to find a particular solution. So we need to pick something that looks like t. Now what looks like t is a line. So like look at it's a line which is mt plus c. Now I reckon I'll probably be using ct plus d in the notes. Okay, so the problem is finding a particular solution. According to the table and the philosophy, we try a trial solution ct plus d. Differentiate that once, you get the constant c. Differentiate again, you get 0. So now we're going to try and put in these bits of information, the trial solution, the first derivative and the second derivative, into this differential equation and try and get out t. So let's see how we get on. So we have second derivative of the trial solution plus 4 times the derivative of the trial solution plus 8 times the trial solution. What do we get? So the second derivative is 0. The first derivative is c plus 8 times the original function that we're trying here is ct plus d. Now we're trying to make this equal t because we're trying to get this thing to solve the differential equation. So we want this to equal t. So what we're going to do is we're going to multiply it out and look at the t's and the constants. So if I look at the t's, I have 8ct. If I look at the constants, I have 4c plus 8d. I want this, that's not the color I wanted. Want this to equal t. Now think about what t is. T is 1t plus 0. So what I want is, if I want the thing on the left hand side to equal the thing on the right hand side, I need this to equal 1. So I'll have 1t on the left, and I want this to equal 0. If I can find c and d that does that, then I have a what's called a particular solution. Are we going to solve that on the next page or here? Okay, so down here. So we need to solve this. So the first bit is kind of easy enough. Divide both sides by 8. C is equal to 1/8. Therefore, 4c plus 8d, which is equal to 0. I know what c is. I'm trying to find d, so take away 4c from both sides. 8d is equal to minus 4c, but c is equal to 1/8, so if 8d is equal to minus 4 by an 8 is minus a half. And now if I want to solve for d, I divide both sides by 8, so I get d is equal to minus 1 over 16. So if c is equal to 1/8 and d is equal to minus 1 over 16, I have a particular solution. I think I'll write that down here. So the particular solution, ct 1/8 t plus d minus 1/16. Now what I have to do is I have to add together the homogeneous solution plus the particular solution, and that's the general solution. So let's write this down. So the general solution, seem to have loads of space here, is the homogeneous plus the particular. I have loads of space there, yeah. So, well, no, I'm going to just in case, I'm going to do something up here. So the homogeneous solution was e to the minus 2t a cos 2t plus b sine 2t plus c t plus d. Right. Now, the boundary conditions are really, these are the initial conditions, sorry, yeah. So let's see, where the hell are they coming from? Let's go back to the question. So when t is equal to 0, y is equal to 1, and when t is equal to 0, the derivative is equal to 0. Now, what I'm going to do is I'm going to actually differentiate this thing here, the general solution up here, just so I have space. It's going to be a little bit nasty. I'm going to go way over the left. So the derivative of the general solution. So for the first thing, I definitely need the product rule. So this is going to be my u, and this is going to be my v. I also need the chain rule in there. It is messy. So the product rule says, and the 1/8 t minus 1/16 is no problem because it's easy, and it's sum, so I can do it term by term. So the first thing I'm differentiating is everything in the purple. It's two things multiplied together, so I need the product rule. The product rule says it's the first thing by the derivative of the second thing. So we need to differentiate now a cos 2t plus b sine 2t. So we're going to do term by sum, so we do term by term. So first we're going to differentiate a cos 2t. Fixing the a is no issue. And now cos 2t, if it's cos t, the derivative is minus sine t, no problem. But this is cos of a function of t, I need the chain rule. So the chain rule says, so I'm differentiating cos 2t here. Differentiate the outside, evaluate the inside, times the derivative of what's inside. So the first thing is to differentiate the outside. The outside here is cos of x. What's the derivative of cos of x? Minus sine of x. What does the chain rule say then? The chain rule says evaluate at the inside, and then the chain rule says multiply by the derivative of what's inside. And what's the derivative of 2t? Well, I'm going to fix the constant 2, and the derivative of t, which is 1, is 1. So that's the derivative a cos 2t. Similar story, what you're going to get here. Now, notice you end up just multiplying it by 2. So the second one is basically fix the b by 2, and instead of sine it'll be cos plus cos 2t. Same thing. So that's the first thing by the derivative. Second thing, space is going to be tough, that's why I did it up here. Plus the a cos 2t plus b sine 2t times the derivative of e to the minus 2t. Now the derivative of e to the minus 2t, I'm using something from the tables, that the derivative of e to the ax is a times e to the ax. And so I get minus 2 times e to the minus 2t, and then fix the 1/8, and the derivative of t is 1, plus the derivative of minus 1/16 is 0. So it's nasty, there's no two ways about it. A horrible question to put in an exam, but open book, fair enough. Right, So let's do the initial conditions. So the first one is probably not too bad. It says that y is equal to 1 when t is equal to 0. So I'm looking at the general solution at t equal to 0. Now, if it was writing, I'd probably put all the t is equal to 0 in zeros, but I won't do it here. So I get e to the minus 2 times 0. So I'm putting it into the, see where the purple is? I'm putting t equal to 0 into that. A cos 2 times 0 plus b sine 2 times 0 plus 1/8 times 0 minus 1/16. Now, before I set that equal to 1, well, I'll do it now. So that I want that to equal 1. I'm not going to put all of this into the calculator. Like, there's some obvious simplifications. So this thing is minus 2 times 0 is 0. So that e to the 0 is just actually equal to 1. That's 1. Similarly, 2 times 0 here is 0, and cos of 0 is equal to 1. Now, sine of 0 is 0, so this is b times 0, this is just gone. This 1/8 of 0 is 0, and so things aren't quite as bad as it seems. So I get, this thing is 1, so it's multiplied by 1, I don't have to include that. This is a by 1, which is just a. And what have I got? Well, the next thing is 0, next thing is 0, minus 1/16, and this has to equal 1. So I just add the 1/16 to both sides. A is 1 plus a 16th, which is 17/16. Okay, that wasn't too bad. And now what I have to do is substitute in t equals 0 into the derivative, which is the big long thing there. So we'll do that. So the general solution, the derivative of it at 0 is equal to, so I'm going to put in t equals 0 into this long thing. So I get e to the minus 2 times 0. Now I'm going to be careful here. So this first term in the square bracket is a by minus by 2. I'm going to write that as minus 2a by sine of 2 times 0. Okay, and the second thing I'm going to write as 2b times cos of 2 times 0. That's that sorted. The second bracket, now you could say I've already calculated the second bracket because it's the same as this one, but I'll take my time just not to go too fast. This is cos of 2 times 0 plus b times sine of 2 times 0 times minus 2 times e to the minus 2 times 0, okay, plus 1/8, and this has to equal, what's the derivative equal to? It's equal to 0. Okay, now let's see some nice simplifications. This is 1, this is 0, this bit is 1, that'll be 2b. This one goes to 1, and I know that a is 17 over 16. I just found that out. Sine of 0 is 0. This bit goes to 1. So, sorry, that should be 1. So a lot of things kind of simplify here. Don't put all something like that into the calculator, you'd be daft. So that's 1, forget about that, that's gone. So I have 2b by 1, that's just 2b. Now the next thing I just have, what have I got? I've got 17 over 16 inside the square bracket times 1, which is 17 over 16, plus b times 0 is just 0. This is times minus 2, but then it's times 1, so I don't have to worry about that, plus 1/8, and this all equals 0. Now what I'm going to do is I'm actually going to, the numbers here I am going to put into the calculator. I should be able to manage it, but maybe I'm a bit tired. Minus 2 by 17 over 16 plus 1 over 8. So it's actually minus 2 here. So 2b minus 2 is equal to 0. Easy from here. 2b is equal to 2. And divide both sides by 2, b is equal to 1. We probably had space for the derivative down here. Okay, so we have a solution. Y of t, if I can remember it all. So it was e to the minus 2 t. A, which is 17 sixteenths, cos 2t, plus b is 1 sine 2t plus 1/8 t minus 1/16. And so we can analyze what's going on here. So this yoke is a wave. This thing goes to 0, it's a negative exponential, and this bit is just a line. So as time gets big, you're just going to have a line. So y at time big is just going to be pretty much a line. Now the question is, will it have a chance to oscillate, or is the force, the external force, too big? And we see it has no real chance to oscillate. So in this part of y, we can see that y of 0 is equal to 1. If you could zoom in, you could see that it is actually flat there. But what happens is that the force is quite big. Yeah. So y dash, it is actually flat, just you can't see it. Initially the speed is 0, so the spring force dominates it at first, because the external force is also equal to 0 at that stage. However, very quickly the external force begins to dominate, and the spring does something like that. And of course, what will actually happen is, in finite time, the spring will basically break. In finite time, spring breaks, and or goes plastic. And I presume plastic is something that you understand what means that. Okay, yeah, so there we go. So I think we're going to do another example here. Yeah, we'll keep it going. Are we doing 2? Yeah, we'll just do one more, and this will finish this chapter. Well, we're going to have a little revision of the chapter as well. Okay, so solve using only the method of undetermined coefficients, the initial value problem. Now this one, we've got an external force that goes to 0. So what you should expect is the whole solution will eventually go to 0 as well. So first we look at the homogeneous system, and hence the auxiliary equation. So the homogeneous system is the second derivative plus 8 times the derivative plus 7 times y, and I can put little h's there if I want, equal to 0. That gives you the auxiliary equation r squared plus 8r plus 7 equal to 0. Don't seem to have given much space here. Let's factorize this. 1 by 7 is 7. Only factors are 1 by 7 because it's a prime number, and you can make up 8 using a pair of those. So we have r squared plus 1r plus 7r plus 7 is equal to 0. I can take out the common factor of r out of the first two terms. I'm left with r plus 1. And I can take the common factor of 7 out of the second two terms, r plus 1. And now I've got a common factor here between these of r plus 1 times r plus 7 equal to 0. Two numbers multiplied together giving me 0. Either the first one is 0 or the second one is 0. So I have two solutions, r equal to minus 1 and r equal to minus 7. Now they're distinct, that's good. So I have the homogeneous solution then is, so minus 1 is a solution, so e to the minus 1t. So minus 1 is a root of the auxiliary equation, so e to the minus 1t is a solution of the homogeneous system. Similar story with e to the minus 7t, and you can multiply them by constants and you can add them together. Okay, so now you don't find the a and b at this stage because you need to solve the full differential equation. So now we need to, so we've only solved it equal to 0, we have to solve it equal to this. So now we must find a particular solution. So the right hand side is an exponential with this constant of minus 2. We should try something like that. So we try the e to the minus 2t multiplied by a constant. We differentiate that once carefully. Now you would have seen me differentiating things like this. Well, maybe we'll just do it here. We'll just differentiate it once. So the derivative of c e to the minus 2t, how does this work? Well, fix the constant c and then differentiate the function, and the derivative of that yoke is minus 2 e to the minus 2t, and the c by the minus 2 gives you minus 2c e to the minus 2t. Okay, So that's where that comes from. So now we're going to look at the left-hand side of the differential equation, substitute in the stuff through the trial solution, and try and get that 10 e to the minus 2t. Now, if the e to the minus 2t was in the homogeneous solution, we'd have to multiply the trial solution by t, but we don't have to do that here. So let's see, what have we got? So we're looking at the second derivative. This is the trial solution second derivative, plus 8 times the derivative of the trial solution, plus 7 times the trial solution. What are we getting? So the second derivative of the trial solution is 4c e to the minus 2t, plus 8 times the first derivative. So that's 8 by minus 2c, that's minus 16 c e to the minus 2t, plus 7 times the trial, so that's 7c e to the minus 2t, and we want this to equal 10 e to the minus 2t. Want this to equal 10 e to the minus 2t. So we get, I see 4 plus 7 is 11. Minus 16 is minus 5c e to the minus 2t is equal to 10 e to the minus 2t. For these to be equal, the minus 5c would have to equal 10. So in terms of the name of this chapter, the undetermined coefficients, that would be the c here. This is undetermined, and this is how we find out what it is. Divide both sides by minus 5, c is equal to minus 2. So the general solution is the homogeneous solution. Now there's just a small thing to point out here, and just to say that it really doesn't matter. See the way I have the a with the e to the minus t, and here the b with the e to the minus t. It doesn't really matter. I mean, a and b, if you do it, it doesn't make any difference. Like say if I ran this like this, if I did it like this, I'd say I get a is equal to 4 and b is equal to 2. If I run it down below, I'll get a is equal to 2 and b is equal to 4. It'll all work out in the wash. So that's nothing to worry about. So it doesn't matter how you actually write it. Yeah, like what I'm trying to say is it's the multiple of e to the minus 7t. Like b is just some constant. Doesn't matter what we call it as such. Right, so now we're going to have some initial conditions. So at 0, the y value is 0, and at 0, the derivative is 1. So let's see that. Now using the initial conditions. So this one is the first one. So I have the general solution at t equal to 0. So we'll run with, it doesn't really matter. I'll run with how I did it down below. It really doesn't matter. I'm gonna, you know what I'm gonna do? I'm gonna change the one down the bottom, just for the sake of, we won't be confused. So this is A, this is B. So we're looking at A e to the minus 0 plus B e to the minus 7 times 0 minus 2 e to the minus 2 times 0. So we want this to equal 0. So we want this to equal 0. And if I tidy up the right hand side, so all the e to the zeros are 1s. So I have a plus b minus 2 is equal to 0. I add that 2 to both sides. I get a plus b is equal to 2. So that's my first equation of 2. And now I'm going to calculate the first derivative of the general. I should probably just write the general solution up the top here so we have it. So it's like the general solution is a e to the minus t plus b e to the minus 7t minus 2 e to the minus 2t. So I'm going to differentiate that now and set it equal to 0. Doesn't seem to be that much space. So the derivative, the general solution, equal to. So fix the a. The derivative of e to the minus t is minus 1 e to the minus 1t, plus fix the b times minus 7 e to the minus 7t, and then on the last one fix the minus 2, then e to the minus 2t. Okay, now if I evaluate this, That's 0. I'm gonna have to go, no, I'll be okay. So that'll be, now a by minus 1 is minus a e to the minus 1 times 0, minus 7 times b e to the minus 7 times 0, and then the minus 2 by the minus 1 is plus 2 e to the minus 2 times 0. And what does that equal? Well, all of the exponentials to the power of zeros are 1s, so it's minus a minus 7b plus 2, and that's the value of the derivative at 0. And if you look at the question, we want that to equal 1. Now I'm going to make a nice little equation out of that. I'm going to keep the minus a though. Minus a minus 7b, take away the 2 from both sides, I get this. Now I'm going to add the two equations in a and b together. Hopefully I haven't made a stupid mistake. So I add them together and I get a minus a is 0, b minus 7b is minus 6b, and 2 minus minus 1 is equal to 3. Oh no. Oh no. No, I'm adding them together. Adding them. 2 minus 1 equal to 1. Sorry, now I'm being a total dumbass. Sure, if I take away 2 away from both sides, I found a mistake. Jesus, very bad. So this should be 2. This should be 4. No, I'm sorry not to be rubbing it out, but that's what it should be. This should be 4. Then this should be, this number here should be minus 3. And if I add them together, this should be minus 1. My apologies. So divide both sides by minus 6, and I get that b is equal to 1/6. Then go back up to this equation up in the top right hand corner of the screen. A, take away b from both sides, a is equal to 2 minus b. 2 minus 1/6 is 11/6. So look at the blue thing up at the top and substitute a equal to 1/6, b equal to 11/6, and the rest of it is still there, and we plotted it. It looks something like this. So let's see which is which. So there's a few things plotted here. It's hard to say which is which. Okay, so we're going to figure. Okay, so the red one is the external force because it's an exponential decay. F external. What was the external force? 10 e to the minus 2t. So the external force is 10 e to the minus 2t. The green thing is the thing that was initially 0. That's the displacement. So that's the y of t. And then the blue thing is the velocity, the derivative. Now let's explain a little bit what was happening. So actually it's a shame we don't have the top of this. It's a shame we don't have the top of this, because I think there's possibly a bit more interesting stuff going on with this. So this is just for me to fix for next year. So what I can explain is kind of what happens when the displacement gets big. When the displacement gets big, why does it reach a maximum? Well, what happens? What happens now? I'm finding it hard to explain myself. So at that stage, I think if we look at the velocity, it's gone negative. Do you know what? I can't explain it, I'm afraid. The only thing I can explain is that the external force goes to 0. That's fine. And so you're just left with you're just kind of left with, so basically after a while, it's just like a normal damped harmonic oscillator. It has a big displacement. It's got some speed, the spring force is coming in, but it's actually over damped, and so it just goes to zero slowly. But I'm afraid I couldn't make much more sense of it. I was kind of blathering on there. My apologies. Okay. So we'll do the summary next.